Hello everybody, welcome back to yet another video. I know I said that in a very rushed tone because we don't have time today. Today I'm not going to be starting a new chapter, but this is almost a revision video that you can see one day before your examinations. For all of you who do not wish to go like 30 to 40 or 1 hour worth of videos, they can just come over here. You guys can come over here, see this video, and we'll be covering only the important points. I repeat, only and only the important points that you need to note in this video. We're going to be starting with the chapter 1 of chemistry. We are again, hopefully we'll finish the whole chapter in a single video. We won't keep part 1, part 2 consisting of 30 minutes each video. That's a complete hour. We'll finish it off in one video and just, common revision basically. We don't need to do anything over here. So without further ado, let's get into the video. Starting off with symbol. So the term symbol, important point, it represents a short form of an element. What is a symbol? A short form of an element, not a compound or anything, not a formula. A formula, a short form would be a chemical formula or a chemical equation. But in this case, it is just a symbol. So for example, the symbol of hydrogen is H, right? So that's the short form of an element. Now, a symbol represents a specific element or one atom of an element, and like for example, S represents sulfur, and it also represents the weight or everything. For example, H, you have the atomic mass and the mass number written on top and bottom, right? So it not only represents a specific element or one atom, it also represents the weight of an element equal to the atomic weight. And we all know we always compare any element for its weight to that of carbon. That's 1/12 the mass of the carbon atom. Now, the introduction to the concept of symbol was basically in 1807. John Dalton, he came up with the figurative symbol. So he thought that we'll represent each symbol by drawing them. But of course, not everyone was an artist. So later, in 1814, Berzelius, that's how I pronounce his name, you can pronounce it however you want. He suggested that a simple system of representing elements would be by taking the first letter of the element, or the first two letters, or the first letter and other distinctive letter in the name, or just taking it by its Latin name. So there were two, English or Latin. It's English or scientific, and the other one was the Latin one. So again, under English or scientific names, it's either the first letter, as in hydrogen, right? Or the first two, as helium. Or it can also be the first letter and another distinctive letter, like magnesium, right? It's not Ma. Well, but it is Mg, so that is magnesium, right? Or the elements can also be called by its Latin name, like copper. Its Latin name is actually cuprum, so we say Cu. Similarly, iron is ferrum. So this is the important part over here, right? So the most important parts in this particular page would be first the definition of a symbol. You can get a 1-marker question saying that what is a symbol and all of that, right? And also the person who actually suggested this way of representing a symbol, it can come like in MCQ form, but since this is a board class, that's the grade 9, you are preparing for boards, and it's basically just the basics of what you're going to give in boards. That's in 10th. It is the board pattern, so you will not have MCQs, so you can leave that. You can just read through that. But in this case, the most important would be, of course, the definition and also the symbols, as in what's its Latin name, like copper, cuprum, all of that, right? You can get a true, false, or, name the following question from this. Moving on, valency, radicals, and chemical formula. So what is a valency? The number of hydrogen atoms which can combine with or displace with one atom of the element or radical so as to form a compound, meaning the number of hydrogen atoms, which can combine or displace with one atom. As in, if I take one hydrogen atom and the number of them which have the ability to combine or displace with another atom of the element or radical to form a compound will be called as the valency. So if I have one hydrogen atom combining with 2 or 3, that would be the valency of that certain element, right? So the valency of all metals and hydrogens are positive, and non-metals is basically negative, all right? One more simple definition of valency could be, it is the combining capacity of an element. But this is also very important, the number of hydrogen and the basic, the basic definition, because normally if anyone asks you for the definition, very likely that you will write the combining capacity of an element, but you can, fill in the blanks question or the name the following question can come from this. So mark it as well, it is important. Just go through it. The number of hydrogen atoms which can combine or displace with another atom or element or radical to form a compound will be called as the valency. Now the valency of metals and hydrogen is positive and non-metals is negative. So again, an important factor which is very easy, so I don't think you'll need to mark it, just go through it, right, because this is a revision class. Then combining one atom of hydrogen, one atom of chlorine. This means one atom of chlorine is being combined with one atom of hydrogen. It has the ability to combine with one atom of hydrogen, so the valency of the element will become 1. Then one atom of oxygen has the ability to combine with 2 atoms of hydrogen, so its valency becomes 2. Similarly, one atom of nitrogen has the ability to combine with 3 atoms of hydrogen, so its valency becomes 3. So now you understand the whole definition happening over here, right? Now the valency of a metal is the number of electrons lost per atom of the metal. So as we just saw right now, that the valency of a metal is positive and the valency of a non-metal is negative. Now when it is considered as positive, that means in an atom you have protons, neutrons and electrons, and protons is a positive charge and neutrons is a negative charge. These are the two main charges because the neutrons are neutral, right? So when I say something is positive, this definitely means that the proton charge is more, right? The proton charge is more. So the valency of a metal is the number of electrons lost. Of course, the electrons have to be lost for us to say that the metal is positive. Its valency is positive. Why? Because the proton's charge, its rule has to be more as compared to electrons. Similarly, in non-metals, the valency of a non-metal will be the number of electrons gained. Why? Because it is negative. That means electrons have to have a higher rule. It has to be more than neutrons. It has to have a higher charge. But this does not take away from the fact that atoms, some or the other way, it wants to attain a stability, and it wants to become electrically neutral. But in the state that is in, we consider it as positive and negative. So in this also you have univalent, divalent and trivalent. Stands for its name, uni meaning 1, di meaning 2, tri meaning 3, and then so on, poly, tetra, all of that, right? Now, this is fine. Moving on to the next thing, that's the variable valency. So certain metals exhibit more than one valency, showing variable valency. Now, why is variable valency shown? So an atom of an element can sometimes lose more electrons than present in its valence shell. So loss from its second last shell, and hence exhibit more than one variable valency. This means that sometimes atoms have the ability to lose or gain more than one electron, right, present in its valence shell. For example, in cuprous and cupric, it has variable valency. One is 1 plus, the other one is 2 plus. So its original electronic configuration is 2, 8, 18, 1. But the outermost shell has 1 electron and the second last shell contains 18 electrons. But the second last shell has not attained complete stability, so it jumps. Right? So one electron jumps to the other electron, thus this is called as variable valency. So it has the ability to lose or gain one or more electron, and that is variable valency. Also a very, very important thing. So you can mark it. Okay, moving on to radicals. A radical is a group of atoms of elements that behave as a single unit and show a valency. So a radical is a group of atoms of elements atoms of elements. Elements are atoms, atoms are elements. Atoms are dependent in nature. That's why they combine together to form an element. Always remember that. That is why we say atoms of elements. So a radical is a group of atoms or elements. You can just say a radical is an element or a group of atoms that behave as a single unit. As a single unit. That's an element, a single unit. And they also show a valency. So 1 plus, 1 minus, all of these are basically radicals. They are a single unit, but they also show a valency at the same point. So in this case, we have positive and negative. If you have a negative sign, at the top right, that is negative radicals or negative ions. And if you have a positive one, it is called as positive ions or positive radicals. Okay, moving on to chemical formulas. Again, a very important point. All these definitions are important because you can get 1 marker questions, as I said before, probably fill in the blanks or even name the following from this. All right. Chemical formula, a molecule of a substance that is elements or compounds could be represented by symbols. Right? So I told you before that symbols are nothing but short forms of elements. But what about molecules or just chemical equations in general? What will happen to those? So a molecule of a substance that is element or compound could be represented by symbols. Representation is known as chemical formula. An element referred to as monatomic when it exists as single atom and represented by single symbol of that element. Now, we all know when 2 or more elements come together, it is called as compound, but when 2 or more atoms come together, it is known as a molecule. Like H2O is it's a water molecule, right? And all of this come together to form a compound. So, of course, we represent that by a chemical formula. So, a molecule of a substance, that is an element or compound of a substance. So, water as a whole is known as a compound, but one molecule out of that, or one of, if this is water, one of this would be called an element. And if I have several of these compounds or elements coming together to form compounds, if I take one of them out, that will be called as molecules. That's why a chemical formula are molecules of substances, of a substance that is element or compound. They could be represented by symbols. Now, representation of such, representation is known as chemical formulas. So when an element exists as a molecule, a number representing its atomicity is written as subscript after the symbol of the element. Again, the chemical formula, the definition is very important. Okay. Now, subtypes would be element is monatomic when it is single in nature, very easy. When an element exists as a molecule, a number representing its atomicity is written as subscript, like H2, O2, all of that, right? So that is a subscript, and after the symbol, and thereby this represents a formula. So when I have Na only, I will call it that is an element. But when I have a subscript written down, showing that the element exists in the form of a molecule, this is what you call as a formula. H2, that is a formula. H2O, H2O, a water molecule, that is a formula. Chemical formula, right? So when it is existing in the form of an element, when it is existing in the form of a molecule, you would call it as a chemical formula. Now, a compound contains a whole number of atoms of component elements, indicating that the elements are in chemical formula. So a compound contains a whole number of atoms, indicating atoms are in a chemical formula, chemical combination. So we saw when an element exists in the form of a molecule, it is called as a chemical formula. But what if an element is existing in the form of a compound? It is in the form of a compound, like water, H2O. It is a compound, right? So this indicates that the elements are in a chemical combination, and this is called as a chemical formula. A very, very, very important point. All right. Don't get confused between molecular formula and chemical formula, 2 different things. One says about when one talks about elements being represented as molecules, one talks about when elements are in a chemical combination. Okay, so again, just underline, mark, or whatever, just mark this point, all right? molecular formula also indicates the number of units of radicals present in a compound with the proper subscript outside the unit of the radical, that is CaOH2. This means OH2 meaning the whole twice. The whole twice meaning O is also 2, H is also 2. So we're just simplifying it. Like in maths, if you've ever seen when we have 2A plus 2B. And if I want to factorize that, I would just take 2 common and I would say 2 is common, A plus B. Right? I would say 2 is common, A plus B, and then I can send 2 to the other side and the linear equations, all of that sets in. Similarly, in the case of chemistry also, you want everything in a more simplified and easier manner. So in case, instead of writing CaO2H2, we just take 2 common out of O and H and we say Ca bracket OH the whole twice. The whole twice. So the molecular formula also indicates the number of units of radicals present in a compound with the proper subscript outside the unit of a radical. That's CaOH the whole twice. Now, in this page, this is a radical. I'll just, what am I saying? I'm so sorry. Okay, so in this page, this is a valency chart. Just go through it. Basically, just go through it because you have been learning these elements all your life. Pretty easy. Don't worry about it. Till that, we'll just move on to our next concept. Come on, this chapter isn't very hard, guys, okay? So don't worry. Let's be strong, all right? Let me again zoom into this. Okay, moving on to compounds now. So a compound is a pure substance composed of 2 or more elements, of course. It is combined chemically in a fixed proportion. Underline this, fixed proportion. I've already underlined it. You also underline it. I mean, I didn't underline it. My student did. But that's because I made them underline it, okay? So it is a pure substance composed of 2 or more elements combined chemically in a fixed proportion. Now, example H2O, it is composed of 2 elements, hydrogen and oxygen, and it is in a fixed proportion by weight. Now, when we talk about H2O, people may say that, hey, hydrogen is 2, oxygen is only 1. How is it fixed proportion? Well, we talk fixed proportion as of weight. So maybe the weight of oxygen is more than that of hydrogen. So that's why we need 2 hydrogen in order to make it a fixed proportion, right? Now, properties of water are different from those of constituent elements. Now, some characteristics of compounds will be that components are present in a definite proportion, of course. It's always homogeneous. Particles are one in a kind. That means, example is iron sulfide. Composition cannot be varied. It has a uniform composition and it cannot be seen separately. So particles in a compound are one of a kind, for sure. They are coming together to form a useful product. And compound have a definite set of properties, of course. Any compound has a definite set of properties. Water can help in so many things, right? So they have a definite set of properties, and that's why these compounds exist, right? Because they're coming together to form something useful. Now tell me, if oxygen and hydrogen did not come together, we wouldn't be able to live, right? Because we wouldn't have water to survive. So definitely, any compound or any element that comes together to form a compound, they do it for a good cause, a better good cause, right? And then components in a compound do not retain their original properties. That's true. Now, in water again, the most simple and basic example that you will see out there, oxygen needs, right? Any fire, when we need to burn a fire, it can only be done in the presence of oxygen because oxygen is combustible. The fire needs oxygen to burn. But in the case of water, water is used as one of the fire extinguishers because water sets off fire. That's why fire extinguishers or when something catches fire, we quickly run to get water, right? Because water, it burns down fire. Fire goes away with the presence of water. So you can see over here, oxygen is not retaining its original value. It does not retain its original personal property, right? And it cannot be separated. But the compounds can be separated only by chemical means, not physical means, like not hand picking or sieving. I can't take water and sieve it and say that I'll get one hydrogen compound or element and one oxygen element. That will not happen. So it can only be separated by the means of elements. Sorry, what am I saying? It can only be separated by the means of chemical means, basically, right? Okay, come on, hang in there. I'm sure we're making like a world record. Not world record, but the record of FikarNot today. Because we are finishing this chapter pretty much. I mean, we're not finishing the chapter because I'm not explaining that much to all of you. I'm explaining very, very less because, again, you all are in panic mode right now. I understand. I've been there. I've done that. One day before the exam, want to revise or probably even learn, which I hope you're not doing right now. And you need a quick video so that you can fit all of this into your head, right? So I hope this is helping. Moving on to the next thing without any time pass, right? Is a table which you can go through. There's nothing to explain in this basically. It's just the name of compounds, etc. Okay, moving on to writing the formula of chemical compound. So how do you do that? Now, to write the a symbol of the compound, the positive atom is written on the left side and the negative is written on the right side. Important point, note this down. Before that, let me just tell you what is important in the previous page, that is the compounds page. Just note down all the characteristics. You can just go through it because, I mean, we have learned these same things in grade 6 and come on, you're in grade 9 now, right? So I think it should be easy. And also, a compound is a pure substance. It is combined chemically, so you can mark both of that as well. Apart from it, it is all good, nothing else, right? And of course, the whole table is very important. Every single thing in that is important, all right? So there's nothing, we don't need to mark anything over there. Just note that every single thing over there is important. Moving on, again, let's come back to the formula. So first, the positive one is written on the left always, and the negative is written on the right. Now, if you switch all of this, you will result in a loss of marks, right? Your paper will result in a loss of marks. So just underline the word positive, left side, negative, right side. Okay, so just highlight that. Then step 2, write the valency numbers. That's true. So for example, if I'm taking calcium and sulfite, right? I'm taking calcium and sulfite. So now the the valency of calcium is 2 plus and sulfite is 2 minus. Now, I'm writing the valency number and I'll interchange, like cross multiplication in maths. Once I do that, now if I have 2 on both sides, I'll cut them both and I'll get CaSO3. But if in one side I have 1, like in CaHSO3, right? Calcium is 2, but HSO3 is 1 minus. So what do? The one of the, HSO3 goes to calcium, and the valency of 2 from calcium goes to HSO3. So it becomes CaHSO3 the whole twice, because it's much more easier that way, right? Because we cannot write this because it is a compound. So we just write the whole twice instead of that. Okay? Then rules is first. Now these are just some rules that we can go through. First rule is that when a metal and non-metal are combining, metal is written first and non-metal is given with the suffix "ide". The why am I saying metals? Metals, sorry. So metal and non-metal, when they're combining, the metal is written first. For example, potassium iodide, and iodide, the IDE, the suffix is given. So iodine turns into iodide. So never write a compound name as potassium iodine. No, right? Potassium iodide. Then when this isn't the case when you have one metal and one non-metal. Now when you have two non-metals written side by side. They're given side by side. For example, dinitrogen or dinitrogen oxide or nitrogen monoxide or dinitrogen trioxide, like this, right? And when you have two elements and oxygen, so two elements are written side by side and oxygen is written after that with a suffix "ate" or "ite". One with more oxygen will be "ate", one with lesser oxygen will be "ite". For example, sulfate, sulfite, and potassium chlorate, chlorite. So in this case, potassium and chlorate, they are two elements, right? Or chlorine. But they also have oxygen. So 8 and 8. 8 and 8 represent that this basic compound has oxygen. Then elements also are given suffix like hypo and per, depending on the oxygen content. So hypo is less, per is more, and these were your certain rules. Now, important points in these. First thing, positive atom left side, negative atom right side. Valency, step 2 is very easy. Step 2 and step 3 is very easy. Thing that you've always been doing, so I don't think so I need to tell that to you. Now, in the case of rules, just mark metal and non-metal. Metal is written first and non-metal is given a suffix "ide." Then, two non-metals, they're written side by side and they're given the suffix mono, di, tri. And two non-metals, they're written side by side and oxygen is written after that. They're given a suffix ate and ite, chlorate and chloride, basically. Okay, so hypochlorite, chlorite, hypochlorate, and all of this. All right. Okay, just bear with me. Oh, come on, we're almost done with the complete, like literally the complete chapter. Finally, okay. Now the next 2 pages that talk about the important formulas and important formulas continued, just go through it once again. It's a very easy concept and there's again nothing really a lot to explain in it. So I won't really explain anything in that. You can just go through it according to your own convenience. Now let's move on to chemical equations. So a chemical equation is a shorthand form of a chemical change. It is a shorthand form of a chemical change. So far we have looked at symbols representing elements, then chemical formulas, an element in the form of a a molecule or an element that has gone through a chemical change. That is called, so it is in the form of a compound. So that is called as a molecular formula. Now we look at chemical equations where it is a shorthand form of chemical changes. So if any chemical changes are taking place, we'll call that entire thing as a chemical equation. Now one thing to note is we are going progressively above. Element and then first element only, that symbol. Then element in the form of molecule or compound. Then we are going even more above, and in this case we have several compounds in a certain complete line, and this complete chemical change is called as a chemical equation. So a chemical equation shows the result of a chemical change in which first you say the reactants, as in the two compounds that are reacting together, and also the products. So symbols in this case and formula is used, both are used. So symbols are used of certain like individual elements, and at the same case and at the same time the formulas are also used, right? Now reactants, the substances which take part in a chemical reaction, they're connected with the plus sign, and the products that are formed as a result of the chemical change. Okay, now some examples of a chemical equation is one reactant and two or more products, two reactants and one product, two reactants and two products, two reactants and 3 or 4 products. Now one more important thing to note, just like extra knowledge, one reactant and 2 or 3 products would be called as decomposition. 2 reactants and 1 product would be called as combination. 2 reactants and 2 products can be called as displacement. 2 reactants and 3 or 4 products can be called as, again, like, combination. And not combination exactly. You can say probably like double decomposition or something like that. Or complex, sorry. Totally slipped out of my mind. I'm extremely sorry. 2 reactants and 3 or 4 products can be called as complex reactions. Now, information and limitations of a chemical equation. Information provided is the chemical nature, that's of reactants and products, the nature of elements and radicals involved, the direction of the reaction. And so chemical nature, meaning what nature is it in, then the nature of the elements and radicals, the direction, the state of matter. The limitations is the concentration, the speed of reaction, the change in color, and all of that. So a chemical equation only does not tell us about the concentration, as in how much you're putting in, the speed, as in how long it took, the change in colors affecting and occurring, the completion of the reaction, as in is the reaction completed or not, right? You have the products, but how do you know it is present? Is it completed or not? They don't tell you, right? And also the changes in the evolution of light or sound energy. Now, during the occurrence of a chemical reaction, they do not tell you that they do not tell you the change of the evolution. They will tell you the evolution, but they won't tell you the change in the evolution. Now, moving on to the balancing of chemical equations. I just need a breather. I've I've been talking too much. Okay, before we go on to balancing of chemical equations, or wait, let's just do that first. Okay, so what is a balanced chemical equation? A balanced chemical equation is where the number of atoms of each element is the same on the side of the reactants and on the products. Both of them are same. Now, why should they be balanced? It is because of the law of conservation of matter, which explains that matter is neither created nor destroyed. And an unbalanced equation would say that atoms have been created and destroyed. Right? Now, how is an equation balanced? There is no definite rule, but normally people use the hit and trial method, and that's what I used to. Normally, that I know everyone around me, they also use the hit and trial method. Now, in order to balance an equation, the formula of the equation has to be taken place. Then you have to go through each and every element and see if each and every element is balanced, and that's when you're justifying or giving justice to the law of conservation of matter, and you're also giving justice, or you're basically just balancing the equation, right? Okay, I'm back. I literally just had to pause and run away because I need a breather. Okay, moving on. Just bear with me. Come on, like probably 5 to 10 more minutes. Imagine we had to complete this, like we completed this entire chapter in say like 2 videos. Now we're completing it in 1 video. This is a one-shot video. Okay, now the important things that you have to mark in this particular page. A chemical equation, the name, then the examples, the names that I just told you, not given in your textbook, but I mean, it's always better to learn a little extra. The chemical nature, so the information is provided, the limitations, and also one very important thing would be the law of conservation of matter, right? So these are the most important points throughout the page. Okay, fine. Okay, moving on to the balancing of chemical equations. Okay, hit and trial method, very easy. I don't think so I need to go through that because hit and trial method basically just consists of the counting of the number of atoms. You don't even need to mark this because we've been doing this from very, very young age. Then the partial equation method, I won't be going through this because normally I use the hit and trial method and you guys should too. It's a very original method and there is nothing you have to learn a lot in it. So don't go through it, and neither will I now, because it depends on what method you choose. So if you want to go through the method, you sure can, but I'll always suggest for you to go through the hit and trial method. Okay, so I won't be discussing that. As I said, the reason earlier. So I'll just directly go into the relative atomic mass and relative molecular mass. Okay, fine. Relative atomic mass and relative molecular mass. Relative atomic mass and relative molecular mass, that's RAM and RMM. RAM and RMM. Almost sounds like a rap, right? So atoms are extremely small and very lightweight. Hence, it cannot be weighed directly. Indirect methods have been utilized to determine the absolute mass of an of an atom. So basically, it is very, very hard to weigh an atom. Why? Because an atom is, as we know, you cannot see it with the naked eye. You need a microscope and all of that to actually see an atom. So what do? So indirect methods that only include a paper and pen and a few other basic factors of atoms and facts of atoms. You just need that, and indirect methods like these have been used to determine the absolute mass of an atom. Now, the relative mass of an atom is hence considered by considering a mass of a light atom and relating it to the other atoms or molecules. That is the RAM method. So in this case, what you do is you take one atom, you compare it to the mass of another atom, like 1/12 the mass of one carbon atom, that's C. That's 1/12 of the carbon atom. That's RAM. So you're comparing it, right? And hydrogen atom, being the lightest atom, was initially chosen for this as the standard unit, and masses of other atoms or molecules compared to it. But carbon-12 atom, the isotope of carbon, was later in 1961 considered the standard comparison of masses of other atoms of molecules. Now, the relative atomic mass in RMM. That's RAM and RMM, we'll look at that. So RAM is the atomic weight of an atom, is the number of times one atom of an element is heavier than 1/12. So RAM will be mass of one atom divided by 1/12 the mass of one atom of carbon. So the relative atomic mass of an element expressed in grams is known as gram atomic mass or gram atom of that of an element. Then we have RMM. So REM, what's the full form? Atomic mass. RMM, what's the full form? Molecular mass. Therefore, in this case, we talk about molecular mass. So what do? It is the mass of an element or compound. It is the number of times one molecule is, one molecular substance is heavier than that of 1/12 the mass of an atom of carbon. So atom of carbon that's 1/12 the mass of an atom of carbon is the same in both cases. The only difference is one is atom and one is molecule. And in this case, we call it as gram molecular mass. And in the other case, we call it as gram atomic mass. So the relative molecular mass of a substance expressed in grams is known as gram molecular mass. Now some molecular and atomic weights are given below. You can just go through it. I can't really explain anything in this, right? Then the atomic weights are expressed in AMU. So the atomic weights are expressed as simple. In AMU, atomic mass unit is defined as 1/12 the mass of the carbon atom. Atomic weight of oxygen is 16 AMU, and that is the weight of an oxygen is 16 AMU on the scale on which carbon is 12 AMU. Now, the molecular weight of SO2 is 64 AMU. One molecule of SO2 is 64 times as heavy as 1/12 the mass of the carbon atom. Now, basically, in this case, they're just talking about at what terms is the atomic mass measured. That's AMU, and atomic mass are also not whole numbers, basically only that. Okay, again, not a lot to explain in this case. You can just go through it. We are running short on time, so I'm not running through it. I'm just, as I said, going to be going through the most important points. This is just, you can read it. You can't really learn anything in it. So just go through it, as I said. Coming to the most important points, first thing will be the points relating to atoms. Then RAM, RMM. Then gram atomic mass and gram molecular mass, then the whole table. And this you can mark, but it's just like a read-through, not a lot it doesn't have a lot of content. So I'm sure if you read it also once, you'd be good to go, right? Moving on. Now let's come to some calculations. So we're only left with calculations now, which will not take a lot of time. Hopefully, fingers crossed. I do not want to be overconfident over here. So it won't take a lot of time, just hopefully. And we will be doing the calculations, the percentage composition, and also the relative atomic mass. All right. Now, to move on with this, let me zoom in for you over here. Okay, fine. So let's start off with the relative molecular mass first. Then we move on to the percentage composition. And also comment below if you want a whole, a question session video where I'll discuss almost all the questions. I will not let you go away without any homework. I will give you homework, but it will be a complete question session. So tell me if you want a video like that. I'll be more than happy to make that. Okay, now we don't have time. Let's rush. Okay, now how do you calculate the relative molecular mass? So in the case of RAM, we're only talking about the atomic mass. They're dividing it with 1/12 the carbon atom. But what about the RMM value? So the RMM value will be more easy to calculate, so we are going to calculate that. Now, in the case of RMM, you will be given the atomic weight of each atom, and then you will find the molecules, because two or more atoms together form molecules. So let's say the atomic weight of nitrogen is 14. Now, I'll take my time on this because everything is important in this. I'll only go through one example, and I think that's it, right? Atomic weight of nitrogen is 14. Atomic weight of oxygen is 16. Now, the molecular weight will be atomic weight, the molecular weight. So what are we finding the molecular mass of NO2? So N in this case is nitrogen, right? And its atomic weight is 14 plus, and it has only one atom. So 14 plus, oxygen has NO2, so 2 atoms. So 2 into 16, which basically gives you 46. So you see, in the case of molecular weight, you can take the atomic weight and actually calculate something. But in the case of atomic weight, there's nothing much. You just have to divide, right? So that's why we are taking the method of molecular weight over here. Now, how do you find the percentage then? So in the case of percentage, first, you find the total molecular weight. So if CO2 is 44, Fine. Now, if I want to calculate the percentage composition of CO2, that means how much percentage of carbon do I have and how much percentage of oxygen do I have to make this complete 100% compound. So what do? The basic formula. Now, the molecular weight or the atomic weight of carbon is 12, divided by the total sum, which is 44. Now, let's take in the terms of maths, okay? Now, you have 12, 12. So, a person, carbon scored 12 marks out of 44 marks in a test. How much percentage did carbon score? 12, right? 44 marks is the total marks in the unit test. He scored 12 marks out of that. 100%, how much will it be? 12 into 100 divided by 14. 12 into 100 divided by 44. That means you have 27.27% of carbon, and that will be the RMM value of carbon. Now, similarly, in this case, CO2, I have 2 oxygen atoms. That's 16 into 2. 32. 32 divided by 44. So, oxygen is a more studious person, is a more studious student. So, oxygen scores 32 marks out of 44. So, if I had to find the percentage, it would be 32 divided by 44 into 100, which equals to 72.73% of oxygen. Basic maths happening over here. There's not even any formula required. Okay. Now, I may actually create a complete video on this. So, and with this, it's one short video. If you have any doubts, post it in the comment section below. I'll be more than happy to solve them. Until then, bye.